So continuing with the compression members, today my lecture will be on how to design a compression member. So the given problem is design a single angle iron section to be used as a strut in the roof truss. The length of the strut is given as 1.75 meter and it's subjected to axial compressive load as 1 into 10 raised by 5 Newton. Assume compressive stress and check for the safety of the strut under given loads. So the given data here is load as 1 into 10 raised by 5 Newton and length of the strut is 1.75. So for designing the compression member, step first will be our calculation of gross sectional area. So gross sectional area is equal to axial load by permissible compressive stress. If the permissible compressive stress is not given, you can assume it as 80 Newton per mm square. And our given load is 1 into 10 raised by 5. By this assumed permissible compressive stress as 80, it comes out as 1250 mm square. And on changing it into centimeters, you will get it 12.50. Now our second step will be to choose a trial section. You have to choose a trial section, and the trial section you can choose from the steel table. Step second is choose a trial section. So you will you will choose this trial section from steel table. So refer to page number 32. You have to choose a trial section which will have area either equal to this cross sectional area or greater than cross sectional area. So here we will choose try Indian standard angle 80 into 80 into 10 mm. So this is equal angle section. Both the legs have equal dimensions and this 10 mm will be your thickness. Now the properties which you will get from steel table. Properties of trial section you will get from steel table. So first you will get area as 15.05 centimeters. You can convert it into mm. And radius of gyration along x-axis, radius of gyration along y-axis is same and is equal to 2.41 centimeter. You have RUU 3.04 centimeter. You have RBB as 1.55 centimeter. Now you have to determine the minimum radius of gyration. As you know, the minimum radius of gyration is designated by lambda and it is defined as effective length of column divided by minimum radius of gyration. Minimum radius of gyration. It is the least value of these four. Slenderness ratio. Sorry, this is your minimum radius of gyration. R minimum, this will be the least value of the four. Now we will get step 3 will be your slenderness ratio. Calculate slenderness ratio. Slenderness ratio is L effective by R minimum. L effective, you know it is 1.7 meter. You will convert it into mm. You will get 1750 divided by R minimum, that is 15.5. On calculating you will get as 102.90. Now you got the value of lambda as 112.90. On the basis of this lambda you will have to determine the permissible compressive stress. But for determining the permissible compressive stress, you should know the grade of steel. Lambda is 112.90. The grade of steel is not given. You can assume it as, assume steel as 250 Newton per mm square, right? Now for determining the compressive stress, permissible compressive stress, you have to refer to IS 800. That's code of practice for steel structures design. Here lambda is 112.90. It lies between 110 and 120. When your lambda is 110, your sigma AC compressive stress is equal to 72 Newton per mm square. On this value you have to determine. You don't know the value. You can get it by interpolation. And the sigma AC is 64 Newton per mm square. These two values you will get from IS 800. So on interpolating these values, you will get sigma AC as 69.68 Newton per mm square. Interpolation I have taught you in last lectures. Now step 5. Step 5 is you have to calculate safe load carrying capacity. The formula for determining the safe load carrying capacity is sigma AC into area. Sigma AC is here given as 69.68 into area which you got from steel table, that is 1505. That will come out as 104,868.4 Newton. That is greater than the applied load. Applied load was your 1 into 10 raised power 5 Newton. Means when your calculated safe load is greater than applied load, that means your structure is safe. If the applied load will be greater and the safe load carrying capacity will be less, your structure is unsafe and your structure is going to collapse. Now step 6. Step 6 is check for maximum slenderness ratio. Step 6 is your check for maximum slenderness ratio. You know, slenderness ratio is the effective length by minimum radius of gyration. Check for maximum slenderness ratio. Your slenderness ratio should not be greater than 180. So our calculated slenderness ratio value is 112.90 and it's not greater than 180, means it's safe. Hence our design is safe. Now your step 7. Step 7, it's design of end connections. Design of end connections. You can design the connections by riveted end connections, Second is your welded end connections. These connections I have taught you in, I guess, first unit. Now you can design your end connections either by riveted end connections or welded end connections. Now first we will design by riveted end connections. First is your design of riveted end connections, right? In design you should remember it. If any data is missing, you can assume it, like you assume permissible compressive stress, you can assume diameters. So you have to assume 20 mm. You can assume also 22. It's not any hard and fast rule that you have to select only 20 mm dia. No, you can assume 20, 22, 24, 26. It's your choice. So assume 20 mm dia. Power driven shop rivets. You can also choose power driven field rivets. that is your nominal diameter is 20 mm. So your gross dia will be gross dia of rivet, that is designated as D, that will be 20 plus 1.5 m. Means the nominal for gross diameter you have to add 1.5 if your diameter is up to 25, and if it exceeds 25 you have to add it as 2 mm, you have to add. So your gross dia will come out as 21.5 mm. So for power driven shop rivets, these values you have to remember. Your shear stress will be, for power driven rivet will be 100 Newton per mm square, and bearings, permissible bearing stress will be equal to 300 Newton per mm square. These you have to remember, and for these refer to table 2.3 of the book. Now we will determine the shearing strength. You will determine shearing strength of one rivet. Shearing strength of one rivet. To determine the shearing strength of one rivet, we have the formula as tau Vf into pi by 4 d square. Tau Vf you have here as 100 into pi by 4 into gross dia. Gross dia is your 21.52. On calculating you will get it as 36305 Newton. Right? Now you have to determine the bearing strength of one rivet. Bearing strength of one rivet is determined by the formula sigma Pf into D into T. Sigma Pf is this your 300 into D is your gross dia 21.5, and T is the thickness of the angle section. You have angle section as 80 into 80 and 80 into 10 mm. These are the dimensions. This 10 mm is your thickness. So on calculating you will get as 64500 Newton. Now you will determine the rivet value. Rivet value is the least value. Of bearing and shearing. So rivet value here will be 36305 Newton. Now after calculating rivet value, you have to determine number of rivets. To determine the number of rivets, you have the formula as load divided by rivet value. Load is 1 into 10 raised power 5 divided by rivet value is 36305. It will come out as 2.75. You will take as approx as 3. Right? Now you will provide 3 rivets. Provide 3 rivets of 20 mm nominal dia. And you will determine pitch. For pitch you have the formula as 3 into nominal diameter, that will come out as 3 into 20 is equal to 60 mm. And for edge distance, it will be as 2 into nominal dia, that will come out as 2 into 20 is equal to 40 mm. Right? Now we will design by welded connections. Design of welded and connections. Design of welded and connections. First is your maximum size of flat weld. Maximum size of flat weld, we have the formula as 3.4 into thickness. 3.4 into thickness of the angle section is 10. So you see what will come after calculation. So minimum size of the weld as per IS 800 you can provide it as 3 mm. Let's assume size of weld as 6 mm. This value you have to assume. S is equal to 6 meter. Minimum value you can take as 3 mm sorry. Now you have to determine effective throat thickness. Effective throat thickness. To determine the effective throat thickness, you have the formula as 0.7 into size of weld. 0.7, size of the weld is 6. It will come out as 4.2 mm. Right? Now you have to assume the value of shear stress for welded connection. This value you also have to remember. Assume the value of shear stress as 108 Newton per mm square for welded connections. Now you have to determine the strength of weld per mm length. To determine the strength of weld per mm length, you have the formula as tau Vf into L into T. This is your shear stress for welded connections. This is the length and this is the thickness. Tau Vf we have 108 and its per mm length you will assume L as 1 and T is equal to effective throat thickness. This will be equal to 4.2. So on calculating you will get 453.6 Newton. Right? Now the total length of weld will be given as load, that is 1 into 10 raised power 5, divided by strength of weld per mm length, that is 453.6, that is equal to 220.5 mm. Approximately it will be equal to 221 mm. Then you can determine the length L1 and L2 individually.